Okay, when we have a collection of point charges, we can easily find potential from the equation. But in some problems, electric field is known or can be found easily. So it is easy to determine potential from electric field. So let's see, the force on test charge Q naught is, and the work done by the electric force as the test charge moves from A to B is given by. If we divide this by Q naught, it becomes the theta between E and dl, or the angle we choose it by. Now compare it with this equation. Work A to B over Q naught is equal to, is equal to VA minus VB. We did it in the last video. Now when we compare these two, the final equation will be VA minus VB. E is the electric force per unit charge on a test charge. If the line integral A to B E dot dl is positive, the electric field does positive work on a positive test charge as it moves from A to B. In this case, potential energy decreases as the test charge moves. So the potential energy per unit charge decreases as well. It means that VB is less than VA. If VB is less than VA, then VA minus VB is positive. It means potential energy decreases and your VA minus VB is positive. Now let's draw a test charge, positive test charge. The electric field of the positive charge is directed away from the charge, and V is positive at any finite distance from the charge. If you move away from the charge, in the direction of E, you move towards lower values of potential. If you move towards the charge, in the direction opposite of E, you move toward greater values of potential. So it means that when you move towards the charge and potential decreases when you move outward. Now look into the case of a negative charge. Let's draw again a negative charge. So the direction of electric field lines is towards the charge. For negative charge, electric field E is directed toward the charge and potential is negative at any finite distance from the charge. In this case, if you move towards the charge, you are moving in the direction of electric field and the direction of decreasing potential. In case of negative charge, decreasing potential means more negative value of potential. Moving away from the charge opposite to the direction of electric field, it means you move towards increasing values of potential. So in this case it means less negative values. So potential decreases inward, it becomes more negative, potential becomes less negative outward. Now the general rule valid for any electric field is moving with the direction of electric field means moving in the direction of decreasing potential. Moving against the direction of electric field means moving in the direction of increasing potential. Now the equation, this equation, this one can be written as VA minus VB TL. This equation has a negative sign compared to the integral VA minus VB is equal to A to B E dot dl, and the limits are reversed in this one and this one. So both of these equations are equivalent, but this equation has a slight different interpretation. To move a unit charge slowly against the electric force, we must apply an external force per unit charge equal to negative of electric field equal and opposite to electric force per unit charge. So VA minus VB is equal to VAB. The potential of A with respect to B equals the work done per unit charge by this external force to move a unit charge from B to A. So the potential, we've already calculated potential due to a single point charge by dividing it with potential energy in a simple way. Now we will use this equation to find out the potential of a single point charge. Now let's draw a positive charge. Let me draw it here. Small positive charge. Okay. Consider a point P at some distance r from charge. Now imagine to move a positive test charge which is at point P from point P to some distance at infinity. Because the path we take doesn't matter, so let's take the simple one, a line that extends readily from the fixed particle through point P to infinity. And we take this distance from here to here, r, and some infinite distance we take r. Because we are taking the point P along the radial line, so the direction of force and the direction of displacement would be along the radial line. Okay, so the electric field is directed radially outward from the fixed particle P. Thus the differential path dl and E has same direction. The angle between them is 0 and cos theta would be 1. Because the radial path is taken as dr, so we will take it as dr, and particle moves from this point P to infinity, distance r to infinity. We can write this equation as the same equation, VA minus VB is equal to F2 RQ over this equation 4 pi epsilon naught r square into dr. Now this becomes this side, V minus 0 is equal to minus Q over 4 pi epsilon naught. Right. And this VB is equal to 0 because it is at infinity. VA is equal to V because potential exists at point P at a distance r at r distance. So in short, you got the same results which you got by using the very simple equation this one here. V is equal to U, potential energy per unit charge, and we find out 1 over 4 pi epsilon naught Q over R. We got the same value because here we are using, we take this distance, this one R, for the whole from here to here, this R becomes R. So it's the same equation, but that was the direct way. This one, we just divide potential energy with test charge. Here we use the electric field and find out the potential. So other thing is one more information this equation give you. This equation shows that the unit of potential difference 1 volt is equal to the unit of electric field 1 Newton per Coulomb multiplied by the unit of distance. Hence the unit of electric field can be expressed as 1 volt per meter. So electric field's units become volt per meter. So in the next video we will discuss one sample problem. So let's move to the next video.